We have been studying data structures for manipulating sets, and we studied unordered lists, ordered lists, and then we began to explore the data structure called search trees, which is a data structure on a set of orderable elements. That is, these elements can be ordered by comparison, and our operations which we intended to look at were find an element, insert an element, delete an element, find the minimum, find the maximum, print in sorted order, then union, intersection of two such sets. These were the operations that we were looking at, and we already found out how to write recursive routines. You can write non-recursive routines also, as you can easily make out. The most crucial one is the find operation. Then using the find, the insert and delete functions, we saw how we would do it. The min and max were just moving to the left or moving to the right, and you could find the min and max elements. And then today we will quickly see what these are and try to see what are the defects of this data structure and improve it. So given a set of keys or numbers or even strings which are comparable, you could set up a tree during the process of insertion, and the tree was ordered this way. Elements which are less than the key element at a node were at the left, and which are greater than were at the right. If you had duplicates, we mentioned that we will put in a counter and increment the counter to store how many such elements are there. And we saw how the find operation looks at the node, and if it is less, if it finds the data value equal to the node, it returns this pointer. Otherwise, it recursively searches on the left or recursively searches on the right according to the value of the variable, value of the key variable. Minimum, maximum. Minimum move totally to the left, maximum move totally to the right, and you can get maximum. Deletion was a bit tricky, where we saw that if we have to delete an element, say like 5, then either on the left or on the right, in the left we have to find the maximum element and replace it and delete that element, or move to the right and find the minimum of the right side, replace it here and delete this element recursively. So we saw the routines for doing that. And now suppose we want to print these elements in sorted order, then the sequence in which we should print it is this, then this, then this, then this, then this, then this, then this, 17, and then 21. The question is how we will get it? We will get it by a simple scheme called traversal. Now there are various ways in which you can traverse a tree. The three well-known mechanisms of traversal are in order, pre-order, and post-order, and all of them vary depending on whether you see the left first or the right first. So there may be two types of in order, two types of pre-order, and two types of post-order. Pre-order and post-order are different. In order may be of two types. Now here, in order traversal means like this. At any node, you are given a pointer to a node. We have seen the node structure before. So given a pointer to a node, you do this. You first, so in order, at a pointer P does this. If P is null, return null. There is nothing to be done. Otherwise you call in order on P left, print P data, and in order P right. What does this mean? Let us work out this in order. So in order routine is this. First complete the in order of the left, then print this, then do the in order of the right. Okay, any questions? So let's follow the scheme quickly. Here, so to do it here, we'll call it here. To do it here, we'll call it here. To do it here, we'll call it here, which is null. If it is null, we don't do anything, we go back. So the call here has done its left part, it will do this. So it will print 2. Then it will do the right part, which is null, which returns. So it returns back here. That means the call to this node has completed its left part. So it will print the node. So 5. And it will call it to the right. Once it calls it to the right, again this will recursively call it to the left. It will come here. This is null, so it will print 6. This is null, so it will go back here. It will print 7. Then this is here. Now here again it will print 9. Go back. This has completed both left and right, so it will come here. This has completed its in order right, so it will jump out of this routine and come here. Once it comes here, the call to the root has completed its left, so it will print data and it will call it on the right. This recursively will call it on the left, which will end up in printing 13. Go back, print this, call it on the right, print this, go back, this is completed, this is completed, this is completed. So by in order traversal, you can number the nodes also. Here we have printed the nodes. There is an in order numbering that you can do, which would number this 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is the sequence. And if you do an in order traversal, so 5 is called the in order successor of 2. 6 is called the in order successor of 5. These are the successors in the in order sequence. Trees are meant to depict other data structures as well, not merely search trees of keys, and we'll come to examples where these things are useful when other data representations end up in trees. But in order traversal and a simple routine like this will give you the sorted sequence in ascending order. On the other hand, if you did the right first and then this and then the left, then you would have got it in the other sequence. You would have got this, then this. So 21, 17, 13, 10, 9, 7, 6, 5, 2. So if you are asked to print it in a sorted order, you would simply do an in order traversal. So the in order traversal which somebody asks you to print in ascending order, in our data structure show tree function, where tree is a pointer to a node which we have defined in the last class. If temp is equal to null, return. Else show tree temp left, printf temp data, show tree temp right. This is sufficient to do it. And what is the time complexity? How many nodes it checks? It checks only the number of nodes in the tree. So it is of order n. Because the number of nodes in the tree, if it is n, the number of edges will be n minus 1. If the number of nodes in this tree, how many nodes are there? There are 9 nodes and there will be 8 edges. In any tree of n nodes, there will be n minus 1 edges. It's not difficult to prove that. You can prove it in many ways, and the simplest proof is by induction. For one node, there is no edge. So it is true, by basis condition is true. So the proof is very simple. For one node, there are 0 edges. Assume it is true for n. So for n nodes, there are n minus 1 edges. Add one node. If you want to make it a tree and connect it up, then you have to add one edge. You cannot add 2 edges, it will not be a tree. So if there are n plus 1 nodes, there will be n edges. So it is proved by induction in a very simple way. So if we do an in-order traversal, then we will get it in the sorted sequence. If you want ascending or descending, you have to choose whether you will do left or right first. Just for completion, what is pre-order traversal? Pre-order is first, see, in order is left node right. Pre-order is node left right. That you print the node, do the left, do the right. And post order is left, right node. Pre-order and post order are useful in other representation of trees, not in such search trees, because here they will not give you exactly what you are requiring. But if you remember, do you remember postfix sequence? A number, suppose an expression 5 plus 3 into, say, into 2. This can be written in postfix notation as 5, 3, 2 star plus. Have you heard of this postfix, prefix and infix notation of numbers, of expressions? And any expression, the advantage of what is the advantage of postfix over normal infix? Suppose in infix you write 5 plus 3 into 2 or x plus y into z. In postfix it will be 5, 3 plus 2 star. The advantage of postfix is no brackets are required. The prefix notation, in the computer a lot of expressions are stored as postfix notations. So trees are not meant only for binary search trees. Expression trees are very famous data structure for storing trees. For example, if you have an expression 5 plus 3 into 2 plus 9, then an expression tree for this is usually the node an expression tree would look like this. This is a different data structure. I am just trying to point out that such expressions are usually stored in the form of trees like this. So this says that to get the value of this expression, you have to first get a value here, then get a value here, and then get the value here. So to evaluate a node here, the evaluate function at a node P, if P is null, you return null. Otherwise, you evaluate, get X, which is the evaluate P left, Y is evaluate P right, and then return X and this operation OP, this may be plus, minus, multiply, divide, whatever, OP Y. This is the recursive condition. You evaluate left, evaluate right, and get OP. This is how you evaluate an expression. And the base conditions are, if this is not an operator, if it is a data, you just return its value. This node may be of type operation or data. If it is a data, you return its value. Otherwise, you do this. Now, given such an expression tree, which is a very common data structure, if you store this expression, if you print out the in-order expression tree, and for every time you print it out, you print out the brackets properly. Okay, that is, in order would be first left side. So here you come again first left side, so you will print 5. Then node, then this side. So to do this side, so whenever you are at a node, you first print a bracket. Okay, so you start by printing a right bracket and then come here. So here you printed a right bracket. Let's start again. You print a right bracket first. First thing you do is print a right bracket, and the last thing you do is print a left bracket first, and the last thing you do is print a right bracket. So, and then do the traversal. So first you print a left bracket, then move left. Here this is not null, print a left bracket, move left. Here this is a data, so 5. Print a right bracket, move back. Print the operation, do this side. When you come here, print a right bracket, move left. Print 3, close it, come here, print this node, then come here, come back. When you finished, print a right bracket. Okay, I should have printed another bracket out here, I missed it out. Then come back, print this, come back, print this, come back, print this. You will get the normal in order expression that we write in fixed notation. If you do a post order traversal, that is left right node, then what would be the sequence? Left, left, left. So this is first 5, right, right, you will come here, then here, left 3, then again here 2, then come back star, then come back plus, come this side, right 9, come this side plus. You will get the postfix notation. What does this mean? 5, 3, 2. So these two will be done first. So these two will be done and you will get 6. Then this and this and this will be done. Postfix evaluation. And then whatever you get, the 5 plus 6 is 11. 11 plus 9 will give you 20. This is how you will get in postfix. And if you do pre-order, you will get the prefix notation. So this is another use of trees as a data structure, not merely as search trees. But let us come back to our concept of search trees. And here, by doing an in-order traversal, we can print the nodes in sorted order. Now, once we can print the nodes in sorted order and we know which is the in-order successor of a node, then trying to do a union operation is not difficult, because if you recall, when we had ordered set of numbers 5, 7, 12, 15, 3, 4, 19, then we said that a union algorithm will be a modified version of the merge algorithm of merge sort. You compare these two and the smaller one we put it in. Similarly, here if we have to do a union of two trees, we just move according to in-order successors and we will be able to get the union very easily, because the in-order successor will give you this sequence. So we can use an algorithm which is similar to that to get our algorithm for union as well as intersection. So search trees have got a lot of potential for solving a number of set based problems, that is find, insert, delete, max, min, print, sorted, union, intersection. These will be done. The potential of using search trees is better than of using ordered lists. Obviously, in the worst case, why should it be better? Because all these operations, union and intersection, will take order n time, where n is the total number of nodes of the two sets anyway. But sorted will also take time proportional to the number of nodes. But these find, insert, delete, min and max are going to take time which is proportional to the length of the longest path in the search tree. And the length of the longest path in the search tree, in the best case and in the worst case, what it can be. Suppose you have a search tree in the worst case, it can be a skewed tree. And a skewed tree has got its worst length of the longest path is the number of nodes. But in the best case, this tree could well have been in a better situation. This tree could have been like this. Now 1, 2, 3, 4, 5 nodes. Given 5 nodes, can you get a tree whose length of the longest path is less than 2? Let us see. For one node, let us see what is the best situation that we can get. Okay, the worst we have found out. But what is the best? For one node, it can be like this. For 2 nodes, it cannot be 0. It has to be at least 1. So for 2 nodes, maybe it will be 1. Now for 3 nodes, the best case can be 1. So for 3 nodes, say 4, 2 and 7. For 4 nodes, it has to be at least 2. So for 4 nodes, it has to be 2. And how long will it remain 2? Up to how many nodes? Up to 7 nodes. See, 4, 5th node, 3, 4, 5, 6, 7. Up to 7 nodes, it will remain 2. From the 8th node onwards, it will again have to be 3. You cannot avoid it. So from 8 up to how many it will be 3? 15th node. So now you are getting the pattern. The pattern is that the best case is for up to 2 to the power, suppose you have got m, okay, take the largest n such that m is greater than 2 to the power greater than or equal to, take the small largest n such that m is greater than or equal to 2 to the power n minus 1. This is going to be the best possible that you are going to get, isn't it? So what is m? M plus 1 must be greater than or equal to 2 to the power n. So log of, so what can you say about n and m plus 1? N is equal to, n must be less than or equal to, so the best case height will always be bound by log m plus 1. So now let us come back to our operations. So in the best case, normally find in an ordered list would take order n time, here it will take order log n time, insert should take order log n time, delete should take order log n time, min and max all log n time. This is best case scenario, this is not the worst case scenario. So in an ordered list it would take n, 1 constant time, min and max constant time. This is n. Here we are trying to say we may get it like this. And if these operations are equal, we have reduced the worst case here in many problems to log n, but we have increased some of them. Now it depends on the frequency in which these operations come, but the question is still this is the best case. So can you modify the data structure so as to ensure that we will achieve this? Search trees where during insertion and deletion you try to make sure that the worst case height is order log of n. It may be twice log of n, but order log of n. In the worst case, this we will try to ensure during every insertion deletion. So we'll have to modify our insertion deletion in some intelligent way. If we could do this, then we would have achieved something important. Such search trees are called balanced search trees, and there are various such balanced search trees. There is not just a single type of a balanced search tree, there are various types of balanced search trees. You will hear of several types of balanced search tree data structures. The earliest and one of the most original balanced search trees was called the AVL tree. It is named after the people who discovered or invented this data structure, Adelson, Velsky and Landis. That is why it is called the AVL tree. There are several other such trees. Among binary, this is a binary search tree. Among binary search trees, the most popular balanced search tree nowadays is called It is a modified version of an AVL tree. It's called a red-black tree. And there are other balanced search trees which are not binary trees. Okay. Such amongst them you have the most famous among them is the 2-3 tree. So these are some names. So we must now understand what they are actually supposed to do. In any balanced search tree, the find operation, suppose it's a binary search tree, okay, the find operation remains the same. There is no change in the find operation in an AVL tree or in a red-black tree. In an AVL tree especially, which is just a binary search tree which is balanced, there the find operation does not change. But how does the insertion operation change so as to ensure that the tree is always balanced? Without going into the algorithm, I'll just take one example and show you what happens. Suppose 5 is inserted, and then after that suppose 4 is inserted. So 4 will be inserted by the normal insertion algorithm like this. Then next say 7 is inserted, then 7 would be inserted here, and every time an insertion takes place, two things are computed: the height of the left tree and the height of the right tree. Okay. And in the AVL tree, the check is height of left minus height of right, the absolute value, that is the difference. Either they will be equal or they will differ by at most 1. They will never differ by 2. That is, you are not expected to have a tree. Here this is a valid AVL tree, but this is not a valid AVL tree, because the height, this is true at every node. This is true at this node, the height of this tree must not be violated. Now suppose here height here is, height of this is 1, 2, 3, height of this is 1, 2, 3. This does not mean that this tree is balanced, because this AVL condition must hold for every node. Alright. So the AVL tree says that at every node the height of the left tree and the height of the right tree must differ by at most 1. You can prove that if this condition holds at every node, then in the worst case length of the height will be order log n. How you will prove it, I'll leave it to you to prove, to see why it will happen like this, if this condition is true. So once it detects, how does it detect? By maintaining a height value at every node, and once the height value of a node is updated, the height value of its parent can be updated. The height of a parent is the maximum of the height of its children plus 1. The height of a node can be recursively computed is maximum of height of left comma height of right plus 1, isn't it? The height of this node is what? The height of this and height of this, take the maximum plus 1. Here it is 3, here it is 2, so this will be 4. So using this height value at every node, the AVL tree does what is called the concept of balancing. Quickly I'll show you. Suppose 12 is inserted, then 5, then 4. This violates the height concept because the height of the right is 0 and this is 2. Immediately it is given a rotate right. This rotate right means move this as the right child of this and move this up. So it converts this to 5, 12, 4. It does a rotation. If it is skewed on the other side, it will do a rotate left. And this, once it rotates it right, and then it will continue to balance the right side. So balancing can, without going into details, just like to point out that balancing during insertion in an AVL tree can also be done in log n time. So during insertion, the total process of insertion and balancing will be done in log n time. Similarly, during deletion, after deletion, if it finds that the height value changes, again that rotation will be given, but in the reverse direction. So the concept of rotation is there both in an AVL tree and in a red-black tree to maintain the balance of a tree. I will not go into details of a red-black tree or an AVL tree which is available in the textbooks because it's a binary search tree and you can have a look at it from any book. Just to give you a flavor that search trees need not be binary trees, we will look at another balanced search tree called 2-3 trees in the next class.